Hey, Physics 30s, how's it going? So today we are going to talk about half-lives. Yeah, I just realized just now that I can resize this window. I was always a small little guy in the corner. I'll make myself a little bit bigger this time. Yeah, so I don't know, talk about half-lives. Most of you probably have already heard about half-lives from Math 3-1. We are going to do the more simplified version of this. It's not assumed that you would have done or actually have to do Math 30-1 to be in Physics 30. So you wouldn't know all the log laws. And you learn the log laws in Math 30-2 as well. But it's also not assumed that you've done Math 30-1 at this point. Right? You could either be doing it or you could be doing this grade 11 and Math 30-1 next semester. So we're not going to solve half-life equations using logs. I'll talk about how we're going to solve these questions without logs. It's actually pretty easy. The limitations of the kind of questions I can ask you allow a simplified version of these kind of questions here. Okay, so a half-life question, or half-life, what half-life represents, it's the amount of time it takes an element's activity or radioactiveness to disappear to half as much as it was before. It doesn't mean that the radioactivity is gone completely, because it could decay into something else, which is also radioactive. But that element, that isotope that we're talking about, that isotope has decayed to half of what it was before. Okay? So we can express activity and radioactivity in multiple ways, right? It says here 2 ways, but technically there's lots and lots of different ways you can express this. And there will be a Google video, or sorry, a YouTube video that I'll show you, or a link in the classroom that talks about all the different ways you can measure activities of radioactivity. Like you can measure it based on biological effect, on just plain activity count, how many decays per second. I can't remember, there's like 4 or 5 different ways you can measure radioactivity. You can also just measure it by the mass of the element that's left over. Right? So here we're talking about becquerels. Becquerels is the more common way to do this. It's just usually the decays per second. You can measure these using a Geiger counter. Those are the little click, click, click sounds that you hear in the like Chernobyl and those kind of movies where they're going around measuring radioactivity. They're measuring the types or the amount of decays per second there. So becquerel a becquerel, a BQ, or 50 decays, just measures any type of decay. It doesn't matter what type it is. It would be alpha, beta, or gamma. I can measure it all, right? So when I talk about 50 becquerels, it doesn't really necessarily mean how dangerous it is. It's just how much is it decaying. So half-life, like I was saying, is just the time, a measurement of time, right, that it takes for 1/2 of the element to decay to its next level. Not just decay completely to a stable element, to its next level. So remember when I was talking about decay chains, uranium can decay to something else, and then it could decay to something else, and then decay to something else, multiple different chains until it gets down to lead. But each one of those little steps has its own half-life to get to that next step. Okay. Carbon-14, a very common one, carbon-14 that we'll see a lot, has a half-life of 5,730 years. This is used like in carbon dating. So as an animal lives, you're ingesting carbon all the time. You're not just ingesting carbon-14, you're ingesting all types of carbon. Remember on the periodic table, the number, the 12.01 that's on this periodic table here, my face disappeared there for a second, that number there, I don't know if you can see it, but the 12.01 that's there, that is the average of the isotopes. So when you grab a bunch of carbon in your hands, or you eat plants or animals, you're ingesting carbon. You're ingesting the average carbon, which has bits of carbon-14, bits of carbon-12, bits of carbons, other types of carbons. It averages out to 12.01. So as you're ingesting this carbon, your body is storing this carbon-14 into its growth, into its bones, into its flesh, right? So you have carbon-14, you have radioactive elements inside of you. It decays over 5,000 years, so you don't really notice it too much. But knowing how big you are, a scientist can estimate how much carbon-14 you had at the moment you died. Because once you die, you're no longer ingesting carbon-14. You're no longer ingesting anything. So they could estimate how much you had the moment you died based on how large you were. And then doing some sophisticated measurements of radioactivity, they can determine how much carbon-14 you have now. Right? And then they can see the difference between the two, knowing the half-life of carbon-14, determine how old you are. And that's how we determine how old dinosaurs are and certain rocks and other things like that. Polonium, you can see polonium-214 has a much smaller half-life, like 164 microseconds. That's true. Okay, that's good. But maybe its next step down has a much longer half-life. We don't know. Okay. Well, we do know, but I don't know off by hand. So a typical half-life equation or graph looks like this. Okay? So as you start off here, it looks like talk about iodine 131. So some isotope of iodine is being measured to have 2 milligrams. And then how much iodine 131 is left over is measured as it goes through. Maybe the next element down is a gas or something and it releases, or it separates it. We could just kind of move that piece away from the iodine 131, or we could filter it out and then measure what's left over. So we can measure all this iodine 31. And then you'll notice here that by the time it gets to 1 milligram, which is half as much it was before, that was 1, 2, 3, 4, 5, 6, 7, 8 days. So this is one half-life in length. Now, the 8 days, it really doesn't matter if I start off with 2. If I start off with 200 or 300, the time it would take to get to half as much as it was before is always going to be 8 days. You can see in the next step here, they did a bunch of measurements afterwards, and they said, okay, from 1 down to half of 1, which is going to be 0.5, this time, if we just move our x-axis, or sorry, y-axis to here instead, that's my starting point, my new starting point. So the time it takes to get to half as much as it was before, another 8 days. So now we're at 16. Now, if I wanted to go down to 0.25, like half of that, it would just be another 8 days later. So over here, this graph would continue down. This distance would also be 8 days. Okay? So every 8 days, you decrease by half as much. Now, the equation for this kind of thing, this is just a typical exponential decay graph you'll see in Math 30s. It's just going to be in the form, like if you think about exponential graphs, it'll be a times b to the power of x, where b is your decay factor. What are you multiplying by each time x changes by 1? So here's my equation down here. Rather than using a, we use n naught. N naught or m naught, one of the two, doesn't really matter which one, is your initial amount. It's where you start, right? Your initial amount. So my m naught and those two, that would be 2 in this previous example, if I were to create an equation for this one. So maybe I will. Let's see what the equation looks like. So my equation that would represent this would be 2 milligrams times a half, because we're dealing with a half-life. Now, if you do a regression for these, most likely this won't be a half. It'll just be some ugly number that just fits this graph nicely. But if I want to represent this using a half-life equation, I put a half in that spot. Now, this up here could be n, right? So down here, that's what n. N is the number of half-lives. And usually how we determine the number of half-lives, it's we take the amount of time that's passed, right? And divided by the period of the half-life. So this is the actual half-life number. So I can determine how many half-lives have actually occurred. So it doesn't always have to be one whole half-life. It could be like a quarter of a half-life has occurred, or 1.3 half-lives have occurred. Sometimes it's nice numbers like 2 half-lives. That's pretty easy. Yeah, so like the previous question, that would be 16 days. The time is the actual amount, the actual time. Okay. Time elapsed. Let's go. Elapsed. Okay, so that's the time elapsed on the top. And we could determine the number of half-lives. I can't remember what's on your formula sheet. Does it put the n there or does it put the t over p? Maybe I should find a legit formula sheet somewhere. Oh, it's right here. Yeah, they just put an n there. So it'd be nice to know that you can calculate the n by going t over p, right? So most of the time when you write these formulas out, we don't write n here. We write t over p, and p being the half-life in this question is 8 days. Yeah, we said it was 8 days before. So I put 8 days there. And I'll just put down here where t is in days. Right. So this would be my equation to determine the mass that's left over. So I can put it in here, and you can see that if I put an 8 in here, the time elapsed would be 8. It'd be 8 divided by 8. A half to the power of 1 is going to be half. Half times 2 is going to be 1. So I'm going to 1 now. If I put 16 there, 16 divided by 2 is, or 16 divided by 8 is, 2. A half squared, because that's going to be an exponent of 2 up there, is going to be a quarter. So a quarter of 2 is 0.5. So that's going to be half. So I can determine anywhere now if I wanted to. I can say, okay, after 1 day, what is this number after 1 day? It looks like it's like 1.8. So I can go back to this equation, put a 1 in there. Put a 1 in this equation. So there'd be a 1/8 there. So 1/8 of a half-life has occurred. Now, the problem with that is it's a little bit tricky to determine without a calculator, because 1/8 technically is like it's an eighth of root of 2. I don't know what 1/8 root of 2 is. So you could pull out your calculator and plug that in there. So that's a nice little equation that would represent this line. Okay. The m and the n's, they could just be interchanged. N is usually activity, m is the mass. Okay, so let's look at this question here. The half-life of the radioactive isotope is 2.5 years. The activity of the original sample is about 3,200 becquerels. What would the activity after 5 years be? So that is only, if you look at this, this is a simple question because they're using nice whole numbers. This kind of question, they don't actually have to use like 5 years. They could say, okay, 6 years, what would it be? After, I don't know what number, I think of like over 1,000 years, what would it be, right? But this one's pretty easy. You could do it 2 ways. You can set up the equation, or you could just do it step-by-step brute force. Because so if I start off, I'll just do the brute force way. So I start off with 3,200 becquerels as time is equal to 0. At time is equal to 2.5 years. What's my activity going to be? Let's calculate the other side. So I'm going to take that 3,200 there and divide it by 2. Okay. I don't know what this is. Typing in something on the other side. Didn't work. Okay, so we get 1,600 becquerels. This should be a Q, not a G. Oh, I don't know what's happening there. Let's go away. There you go, that's better. Okay, and then after T is equal to 5 years, which is another half-life again, right? So this is another half-life, 2.5 years, 2.5 years. We take the previous number, because it happened to be another half-life, and divide it by 2 again. So we get 800 becquerels. Cool. Not bad. Okay. So that's just the brute force way. And it just happened to work out nicely because the 5 is a multiple of 2.5. So it worked out nicely. But you don't always have to be that way. So it could just, this could be any number. So the brute force way wouldn't work. It was like 1/8 of a half-life. It would be hard to do. So we just set up the equation. So we set up, okay, so this is activity. So I'll use N is equal to my initial activity, becquerels, times a half raised to the power of how many half-lives. I'm going to calculate this by going 5 years divided by 2.5 years. We want to make sure those units match up so those cancel each other out. And then I can just do the math. 5 divided by that is 2. 2 times that is a quarter. At any point, I could have just plugged it in my calculator. A quarter times that is 800. Right. So both ways work just fine.